today we'll be doing what might be our last CMPS to 11 revision session. Today we'll be solving this previous, which covers mostly sets and functions. It has a great focus on sets and functions, which we haven't really solved a lot of. Okay. So let A, B, C be sets such that all of them are disjoint. So basically this is A, B, C, and they share nothing in common. All of them are disjoint, right? And they want us to get the intersection between A and the union of B and C. We know that the union of B and C is just B and C. And we want to get its intersection with A, and very logically this should be phi, and I believe here they've made a mistake. It should be the empty set, right? Because A has nothing in common with B, and A has nothing in common with C. So of course it will have nothing in common between it and the concatenation, or like the union of B and C together, right? And you can see it here, so the union of B and C is just B and C, and they have nothing in common. Even you can do, it's equivalent to the intersection between A and B, union the intersection of A and C, right? And both of them are phi. So yeah. Okay, so here we have the function, okay, the inverse of the bijective function. Okay, so we have this function, right? And we want to get its inverse. What does it mean to get its inverse? So let's call f x y, right? And getting its inverse means that we want, given, usually you're given x and you get y, you want to be given y and then to give them x that would have given me this y, okay? So, and why is it important here for the function to be bijective? What does it mean for a function to be bijective? It means that it's a mapping between A and B such that it looks like this. Each input in A has exactly one output in B, and also each output in B has exactly one input in A. We can still get the inverse of functions that look like this actually, because we can pick one of these, right? But yeah, okay, so let's take a look. Now we want that given y, we want to give them the x that would have given me this y had I plugged it into that function. Okay. So basically let's just do algebra, right? We want to have a relation between x and y such that given y, I'd give them x. So let's do this. Y minus, you can think about it like if I tell you x is equal to something, solve for y, you can do it. Okay, so if I tell you y is equal to something, you can solve for x, right? Because we'd have x equal to an equation with exactly one unknown, and we could solve for that one unknown, right? Okay, so y into x minus 1 equal y into x minus, okay, so no, this is x minus 2, and then the one down is x minus 1, right? Okay. I mean, it's equal to x minus 2, and then, or x minus 1, sorry. So x minus 1 minus y minus x equal minus 1, right? So yeah. And then we take x in common. What we're left with is y minus 1 minus y equal minus 1. And then what do we want? We want an equation such that given y, we tell them x, right? So it should be x is equal to something as a function of y. So basically what we do here is 1 plus y over, okay, so this one was actually minus 2, right? So minus 2y, yeah? We're left with minus 2. Okay, so now this would have, okay, let me just check really quickly. It's x minus 2 over x minus 1. This is 2. And then this is, okay, so this multiplied by 1. And this x minus 2. Yeah, so I thought that there was something off. Okay. So basically this is minus 2. And now what we have is, okay, so now what we have is y minus 2, this is minus 2, over y minus 1 is equal to x, and we have it over here. Okay. Okay. And now let's continue. Okay, so here we have f of x, or like f of n is equal to this, and we want it as a closed form equation. So basically I want to give him, if f of n is equal to this product, I want to give him a closed form equation, and the meaning that I want to give him f of n, instead of being equal to this, or like represent this in another form, which is directly plug in n and get the answer, right? Okay, so how can I do that? Basically this is equivalent to 2 summation from 3 up until n of I, right? Because 2 power 3 times 2 power 4 times 2 power 5 is 2 power 3 plus 4 plus 5, right? It's equal to 2 power 3 plus 4 plus 5. And this is in turn equal to the summation from 1 up until n of I minus 2 minus 1, right? Because it's the summation of everything minus the first 2 things, right? So because it starts from 3. And then we can expand this into I plus 1 over 2 minus 6, so 2 power this, right? And then this, minus 3, and then this is I plus 1 minus 6 over 2. Okay, and this is then n, not n. And then this is n squared, and then this is n squared plus n minus 6 over 2. You can see here, if we try to expand all of these, this is the only one that would work. And it's pretty clear, like out of the other solutions, because n into n is n squared, and then we have 3n, and we also have minus 2n, so that's 1n left, and then minus 6, right? Minus 2 times 3 is minus 6. Okay, so this one is also done now. Okay, so now given this function that's just takes x and gives us the floor of x. So the floor of x, if I had 3.33, the floor is 3. So basically just remove the decimal part, right? Okay, so which one of these is true? Usually in these types of questions you can just try out examples. So basically, if I have f of 3x equal to 3f of x, is this true or false? Let's think about this for a second. If I gave you 3.33 and then you multiplied it by, like, not 3.33, so basically 3 plus 1 over 3, right? Then you want, this is x. Multiplying it by 3 would give me exactly 10, right? But then multiplying 3 by the floor of this would give me 9, right? So this is false. And usually the way that you want to pick your examples is usually, like in this part, we're doing like floor operation. So what matters here is really the decimal part, right? So you want to just pick anything with a decimal part that would maybe cancel over here. So like the decimal part will cancel over here, and then look, we'll look and see, will it also cancel over here? And if it cancels, will it give me the same answer? So basically, is there any info that's being lost over this baby, right? Okay, so now f of x plus 3 equal to f of x plus 3, so the plus 3 is outside. Okay, so this looks to be true. Why? Because what we're doing over here is we have x, and let's say x has some decimal part like 3.3, right? Or like 3. Okay, so let's say x is the same thing as before. Adding 3 will not change the decimal part, it will only change the integer part of x. So the decimal part will remain the same. And so always we're removing the decimal part of x. So always what we're doing is we're taking the integer part of x and adding to it 3 on both sides. That's what we're doing, right? So yeah, so this is true. Let's go through the other examples. Here, why is it wrong? Because maybe I had 3 plus 2 over 3, and then I add 1 over 3, and then what I'm left with is 4. But then on this side, right, on this side, I would be left with not 4, right? So on this side I'm left with 4, right? Because 3 plus 2 over 3 plus 1 over 3, its floor is 4. But then on the other side, I have 3 plus 2 over 3. The decimal part is removed by f of x, and then I add 1 over 3. So I'd have, instead of 4, I'd have 3.33, or like 3 plus 1 over 3, right? So the basic idea here is whenever we change the decimal part within the f of x, and we're not changing it on the other side, or basically we're not reflecting that change on the other side, this would be false, right? Okay. So yeah. Now f of x plus y equals f of x plus f of y. This is clearly not true. Why? Because of the one before. Because if this was true, then this would be true, right? Or maybe no, sorry, because no, this is not they're not equivalent. Why they're not equivalent? Because f of my 1 over 3 is 0. So let's think about this. We have x. Okay, so let's call each number like x is equal to x point x prime, and y make it equal to y point y prime. Okay, so each number is an integer and a decimal part, right? Okay. So let's try and continue from here. If each number is an integer and a decimal part, f of x plus y is just x plus y over here, plus any carry from the addition of the two decimal parts, point the addition of the two decimal parts, right? And I'm assuming that we're removing the carry from here. So what I mean by the carry is like maybe they're both 5.5, so it's equal to 11. So it's equal to 5 plus the carry that came from here, which is 1, right? At most you will have a carry of 1. Okay, so now let's look. So if I do this, if I do f of x plus y and the x plus y are on the inside, what I'll be getting is the x plus the y plus the carry, assuming that there is a carry. But if I do f of x plus f of y alone, I'm removing the carry, right? Because if I had 5.5, f of 5.5 and f of 5.5, it's both 5, and then I'll be getting 10. I wouldn't be getting the carry from the decimal part, right? This would only be true if x prime plus y prime is less than 1. Because if it's less than 1, then it's the same. I'll just be adding the integer parts and then removing the decimal part in both cases. Okay. Okay, so now let's continue. Okay, so we're removing both B and C from A. So basically this is A, and we have the union of B and C, which is basically just B and C, and we're removing it from A. This is very clearly equivalent to, sometimes in these types of questions, it's useful not to really think about, sorry, I took a screenshot by mistake, not to really do this stuff, just think about it logically. So then what I have is the set A and the set of B union C, and then I'm removing B union C from A. Isn't that equivalent to removing from A B and then removing C from A? In essence, what I'll be doing is removing whatever intersects between A and B and C, between A and the union of B and C, right? So I'm removing whatever intersects between A and B, and whatever intersects between A and C, and I'm left with whatever is left from A, right? So yeah, it would be this. So I remove B from A, and then whatever is left, let's say I removed B from A. This is A, and this is what I removed from A, which is B. And then C has this part from A. So what I do is, the thing that is removed, I intersect this with the full A, but with the C part removed, right? So the intersection between A with the C part removed and A with the B part removed is A with both the C and the B part removed, right? I hope you understood that. So which of the following is false, not true, false? Okay, so there is a bijection from Z to Q. Why is there a bijection from Z to Q? Because Q is countable. You know, Z is the set of all integers, and the Q is the set of all numbers that can be written as quotients, so like 2 over 3, or like in general, X over Y. So there is a bijection because Q is countable, so there's a bijection, okay. If A, I don't know if you've been taught in class that Q is countable, but if you didn't already know, I think they give it in class. I have such a memory, maybe, but if you don't know why, it's pretty easy. Just look it up here. Why Q is countable, but it's not the correct answer, so we'll be going forward. Okay, so if A is a finite set, then the power set of A is countable. Yes, of course, because if A is finite, then its power set is also finite, because the power set is the set of all, if you wish, subsets of A that I could take. Okay, and so if I had A, B, C, the power set of this would be A, B, B, C, A, B, C, A. So any subset that I could take. But it also be limited, right? Because it's limited by the number of things that were already in A. If A is finite, then this would be also finite. The intersection of two uncountable sets is uncountable. Okay, so sometimes one could think by intuition that yes, if I have two uncountable sets, then the intersection is also uncountable. But sometimes intuition is not enough. Let's try to think about this. We want to get a counterexample because we're looking for something that's false. So basically, we want to look for two uncountable sets such that their intersection is countable, right? Okay, so what two uncountable sets can I find where their intersection is countable? Basically, okay, so what's the simplest uncountable set that one could think of? Usually it's the set of, usually when we think about all rational numbers, right? And any subset of these that is continuous, like when I go from 0 to 1, this is also uncountable, right? Okay, so let's try to find an example. We can do this, right? Because the intersection between these two, both of them are uncountable. Their intersection is 1, which is countable. We're looking for something such that their intersection is finite. And this is a good, that would have been a good example for two uncountable sets such that their intersection is countable and finite. So yeah, this is the answer. And then this is countable. Why is this countable? Because it's n. It's like maybe double the length of n. So I'd leave this up to you. It's not that hard to see why it's countable. This problem is actually a problem that a lot of people maybe got wrong during the exam. Well, it's pretty easy actually. So let's try to solve it. First, it's the inverse of this function. Let's take a look at this function alone. It's a function that takes x. X goes through g power minus 1, gives us y. And then this y is fed through f, which gives us z, right? So if this from here to here is through g power minus 1, then from here to here I can go using g, right? So if I give g, if I plug y into g, I will get x, right? And the same goes for here. So if I go from here to here using f, I can go from here to here using f minus 1, right? What I want is the inverse of this function. The inverse of this function is a function such that given z, it will give me x, right? Yeah, because it's the inverse of a function is a function such that if I give it something, it gives me whatever I would have plugged into the initial function to get this, right? Or to the other function. So here, given z will first have to go through f minus 1, right? And then it will have to go through g. In other words, so z will first have to go through f minus 1, and then whatever this gives me, I should plug into g, right? So then this would be b. Now, okay, so this one is pretty easy. Okay, so we have A, B, and C are sets. You want to show that this is null. Okay, so let's try to do this. It's A minus C, enter C minus B. Just looking at this, we can know that it's null. Why? Because first we're removing C from A, so we have the set that is disjoint from C, and then we're doing its intersection with something that is a part of C, because it's C minus B is a part of C. It's like a subset of C, and we're doing it we're taking its intersection with a set that doesn't have C in it, right? Because we removed C out of A. So just by looking at it, we can see that it's null. Let's try to prove it.
Sure.
So this would be like this, and we have C and not C is null, then anything with null is null. So this is pretty easy. Okay, so this is a question that looks like induction, hopefully not very hard. Okay, so for n greater than or equal 1, we want to prove that this is equal to this. What's going on here is just we're increasing the power of the 2's. Okay, so we have the form here. So so first let's take a base case for n equal to 2, or like n equal to 1. That's pretty easy. Just plug in 1 over here, and you'll see that they're equal. We're not going to do that. What we actually want to do is, given that it works for n, we want to show that it works for n plus 1. Or actually, given that it works for n minus 1, let's try to prove that it works for n. Okay. So actually no, let's do n and n plus 1. So if it works for n, let's show that it works for n plus 1. This is just, it doesn't really matter. It's just what looks easier to do in math. So basically, if this is equal to 1 minus n plus 1 times 2 power n, right? So these two are equal. What do we want to show? We want to show for n plus 1. So let's just add on this side n plus 3, so it's like n plus 1 plus 2 into n plus 1 times n plus 2, right? We're substituting n for n plus 1 times 2 power n. So let's add this term. What we want to show is that if we add this term on both sides, this will become of the form the same, but n plus 1 instead of n. So like n plus 2 over here and then n plus 1 over there. Okay, so let's add this term on both sides. So we have all of this up until here, and then we add plus n plus 3 over n plus 1 into n plus 2 times 2 power n plus 1 equal to this plus 1 over n plus 1, n plus 2 times n power 2 plus 1. Okay, so now on this side there's not much to do. All you need to show is, okay, sorry, it is that at this side we add the same thing, so n plus 3 over n plus 1 and 2. So yeah, basically you want to show that the new term, which is n plus 3 over n plus 1 into n plus 2 times 2 power n plus 1 equal, plus, we want to evaluate this. We want to show it equal to this, but with n plus 1 instead of n. So let's do that pretty quickly. Okay. Okay. So let's try to have the same denominator. We have to multiply over here by 2 and by n plus 2. So after we do that, we'll have n into n plus 1 over 2n plus this, and then plus 2n plus 2. If we calculate this very quickly, we'll have 2n plus 5, or sorry, plus 7 over n plus 1, n plus 2 to 2 power 2n plus 1. Okay, you need to show that this is equal to 1 over n plus 2 power n plus 1. So basically Okay, so what we should have ended up with is n plus 1 on the top and the bottom, so that we can remove it from the top and the bottom, and we left with what we wanted. But that doesn't seem to be the case, because this is minus not plus and we took it as plus. So we're going to have to redo this very quickly. So here we have a minus, and then we're going to be left with, okay, so n plus 3 minus 2n minus 4. So it's minus n plus 1 over this n plus 1 into n plus 2 times 2 power n plus 1. Remove these, and then we're left with minus 1 over n plus 2 over 2 n plus 1. So yeah, that would mean that that would prove it by induction, because we're going to be left with this same thing, but for n plus 1 instead of n. Okay, so this was the hardest question in the exam. He said prove that if a is countable, b is not, then b minus a is uncountable. The proof he wrote here was pretty long and it's unnecessary. At least that's how I remember it. Let's try to remember the proof very quickly. So basically we have a, which is countable, and b, which is not, and then we're going to do b minus a. So we're going to remove a from b. We want to show that this is still uncountable. We want to show that b is still uncountable. Okay, so let's try to do this by contradiction. Assume that this is indeed countable. Then, okay, so if this is countable, then what is this? This is b and not a is countable. And if b and not a is countable, what do we know about b? Okay, but b is equal to b and not a union, right? So we know that b is equal to b and not a union b and a. So what does this mean? If this is countable, and this is also countable since it's a part of a and a is countable, then b would have been countable. So by contradiction, we have proved that that b is indeed uncountable, or in other words, that b cannot be countable. So now for the final question, let x map. Okay, so let f of x to y be a map, or like a function. Show that the inverse of a union b is equal to the inverse of a union the inverse of b. So f inverse of a union f inverse of b. Okay, so when they gave us a very big hint, which is the definition of inverse. So okay, so let's try to think, what does this say? It's trying to say that if I plug into the inverse function of f a union b, it's equivalent to plugging in a into the inverse of inverse function and b into the inverse function. Okay. Okay. So basically, all of this is trying to say is, if I have a and b, and I'm feeding them into f power minus 1, the answer set is equal to. So this is just this. If I take this as a union b, or I take this as a, and then I make it go through the function, and then b, and then I make it go through the function, and then I do the union of the answer, it's the same thing. That's all it's trying to say. So what they told us is, this is the definition of the inverse function. All you have to say is f inverse minus 1 of a union b is equal to the set x belongs to. Okay, so it's the set x belongs to x such that. Okay, so it's not belongs to x, it's the set x belongs to a union b such that f of x belongs in C. Or say, oh, sorry. It's the set x belongs to x such that f of x belongs to a union b. What is this trying to say? It's trying to say that the solution set of f power minus 1, or every answer that could give me, is an x such that if I plug x into f, it would give me something in A union B, right? Because so f power minus 1 of x is y, so f of y is x, right? So what it's trying to say is, if I put here a set, so every answer y that's given by this is something such that if I do f of this, it will give me something in that set, right? So if I'm just changing x into a set, I'm saying that for everything in A, let it be x, so this still holds, basically. So yeah, and then we do the same thing for A and for B. And what this will give me is two sets, the same thing here, f of x belongs to B, to A, and then union one that belongs to x. And so it's x. After this, all we have to say is this is equal to the set x, such that x belongs to x, and x, f of x, belongs to A, or it belongs to B. And saying that it belongs to A or belongs to B is the same as saying that it belongs to the union of A and B. That's all it is.